Now, in the beginning, we have y equals sine of x. Let's consider the graph of y equals sine of x, the sine wave. But there's a problem when we try to invert this and get an inverse function, inverse sine of x. The problem is that even though this graph passes the VLT, the vertical line test, so we have a function here, the problem is that it fails the HLT, the horizontal line test, which means that this function is not one-to-one. It's not invertible. It fails the horizontal line test. I can take a horizontal line here that intersects the graph in more than one point. In fact, infinitely many points. So what we need to do is that we need to restrict this sine wave. We need to restrict the domain of sine of x in such a way that we follow two conditions. What should this restricted domain be? It should be an x interval on which the sine graph, first of all, passes the HLT, the horizontal line test. That means we can take an inverse. That's an inverse function. And it has to be as tall as the original graph, meaning that the range is the same as before. Because I could say, hey, the origin, the point 0, 0, if I grab that, that passes the HLT. But that's pretty lazy. We would like something bigger than just a point. We would like something as tall as the original graph that has the same range, but a piece of the graph that will pass the HLT. So we want a piece of this sine wave that's as tall as the original graph. It has the same range, but passes the HLT, the horizontal line test. Now, we all agree across the planet that we start at this point, negative pi over 2, comma negative 1. And then where would we stop? Well, we want to pick up the entire range, so we have to keep going, going, going. We want the entire range, and we're going to stop where? We're going to stop here, at this point here, at pi over 2, comma 1. Because we want to capture the entire range for the sine function from negative 1 to 1. Technically, it's a new function here because we're restricting the domain. For the original sine function, the range was from negative 1 to 1. The domain was all reals, but we're now restricting the domain to this closed interval from negative pi over 2 to pi over 2. We have the same range as before. Now, we don't want to go any further because then we're going to we're going to fail the horizontal line test. So we don't want to go any further than this point. Okay, so we all agree that we're going to grab this red piece of the sine wave from this point here to this point here. And it goes to the origin, 0, 0. So then, how do we go from this restricted sine function to an inverse sine function? We can invert this because it now passes not just the VLT, but the HLT. So remember a key basic principle. Actually, there are 3 basic principles. The domain of one function becomes the what of its inverse function. The domain of a function, a one-to-one function, like this now, becomes the range of its inverse function. Second, the range of this function becomes the domain of the inverse function. And also, the idea that the point A comma B on the original graph becomes what point on the inverse graph? The point B comma A. The idea being that inputs and outputs switch. So based on this red graph here, how do we invert this red graph to get the blue inverse graph? I'll take a copy of my notes here. And here we go. Again, we switch the domain and the range. Let's look at this grid. The restricted domain for sine of x, we just determined that on Desmos. The restricted domain, the x-coordinates go from negative pi over 2 to pi over 2. The domain for the restricted sine function becomes the range for the new inverse sine function. Likewise, the range for both the original and the restricted sine function, the y-coordinates we pick up, went from -1 to +1, the y-coordinates. The range for the sine function now becomes the domain for the inverse sine function. The domains and the ranges switch. And these are all closed intervals. So observe, the old domain went from -π/2 to π/2. That's the new range, from -π/2 to π/2.